Okay, so we start the clock for the preparation. And during the time, please write down the presenter's name on the board. Okay, the preparation time is almost up. So, reporter, please start your report for 12 minutes.
Okay. Honorable juries, fellow competitors, and most esteemed guests. I'm the reporter for Team Brazil. Today I'm going to report the problem number 9, oscillating screw. And for the problem statement, it states that when placed on the side of the ramp and released, the screw may experience screwing oscillations as it travels down the ramp. And we need to investigate how the motion of the screws, as well as the growth of these oscillations, depends on relevant parameters. And for the phenomenon, first I would like to explain why a screw performs the oscillations on an inclined ramp. And I will simplify the screws consist of the 2 cylinders, and each of them has a different radius. So when the gravity provides the same angular velocity to them, the velocity will be proportional to the radius, so that the bigger heads will roll down faster and cause the oscillations. So in conclusions, we can say the oscillations is caused by the tangential velocity difference. And for this page, in the left, we show the decaying oscillations on the 14 degrees of inclined angle. And for the right side, we show the green oscillations on the 15 degrees. And so we can observe that with different inclined angle, the type of oscillations may be different. And for the force analyzed, we can see there's gravity that acts on the central mass and the normal force provided by the contact point, and also the frictions that cause the rotations. And after analyzing those forces, we can get the degrees of freedom, which will be the position xy and the oscillating angle z and rotating angle theta 1. And since the screw will rotate during the motions, we need to calculate its moments of inertia. And we assume that the screws consist of the cylinders, so the moments of inertia will be like this. And for the rotation axis, along this axis, the rotational inertia will be like this form. And for the oscillations, the rotational inertia will be this form. And for the normal force, since there is no flipping during the motions, so we can consider the static balance along the z-axis, and by this we can get the value of the normal force like this. And for the analysis of the frictions, first we define the frictions as kinetic frictions because the contact point isn't still during the motion. And the directions of the frictions will be opposite to the instantaneous velocity. So we define the central mass direction vector as s and differentiate with respect to it to get the velocity vector. For the head part and the tip part, we translate the vector from the central mass and also consider the extra tangential velocity caused by the rotations. Since the head part will roll down faster, which we have mentioned in the phenomenon part. After we get the direction vector, the frictions can be derived. And after the calculations, we can get the equation of motion by Newton's second law. And for the displacements, we consider the gravity along the x-axis and the component of frictions for both x and y-axis. And for the rotations, we consider the torque that will affect the rotations for both z and y-axis. And for the energy transform, I will use this concept to explain why the different oscillations. When the gravitational potential energy is bigger than the total negative force caused by the frictions, the oscillations will grow. And if the gravitational potential energy isn't big enough, the oscillations will decay. And for my experimental setup, I use protractor for adjusting the incline angle, and I put the board on the protractor to create the ramp. And I use tripod for recording. And these are the dimensions I use in the experiments. And for the measurements of the oscillating angle, which will be the theta z, I use tracker to track both tip and head part and get their coordinates, reduce them, and use arctangents to get this theta z. And to measure the kinetic friction coefficient, I tied up two screws together to make sure there are no extra oscillations. And slide it down from the ramp, track it, and get the VT graph. And use this slope as the iteration, applying this formula to get mu k. And those are the different coefficient of frictions I use in the experiments. And for my first experiment, I changed the incline angle, and it will be the 3 degrees, which represent a very small angle, and the 14, 15, 16, and 18 degrees, and also the 30 degrees, which represent a very large angle. And I will use the theta t graph to describe the different types of oscillations. And the control variables in this experiment will be the radius of the head and the length of the screw, but also the surface, which means the kinetic friction coefficient. And in the videos shown on the slide, we can see with different incline angle, the screw performs the different oscillations. And for the decaying oscillations cases, in my experiments, from 3 to 14 degrees, the work done by the gravity isn't big enough to let the screws perform the green oscillations. And we also saw it will decay. And we have also run the simulations to compare with our experimental result. And what we get is in the trend of the oscillations, the simulations agree with our experimental result. But there is still roughly 2 degrees difference between the experiments and the theory model, which means we still can, in the simulations, we still can see the decaying oscillations that cause in the 16 degrees of the incline angle. And for the green oscillations, if we adding the incline angle to that it reach the critical angle, it reach in this experiment, it will be the 15 to 16 degrees. And the simulation shows that the critical angle will be the 17 degrees. And if we keep adding the incline angle, the screw will finally start to spin, and its oscillating angle will keep increasing like this. And for the explanations, as the incline angle increases, the gravitational potential energy will also increase, so it will cause the oscillations to grow. And for the next experiments, I changed the length of the screw, which will be the 16, 22, 28, and 35, and 41 millimeters. And I will also use the kinetic graph to describe the oscillation. And for the control variables, which will be the radius of the head and the incline angle, the releasing angle, it should be the 90 degrees. And the surface, which means the coefficient of friction. And we can also see the different oscillations caused by the different length of the screw. And the trend of this it will be as the length of the screw increase, the oscillations will decrease. And that's because as the length increase, the moment of inertia will decrease. Will also increase, which we can see in this formula. And as the torque provided by the gravity will be the constant, so as the moments of inertia increase, the oscillating angle will decrease. And for the last experiment, I changed the friction coefficients to see how different frictions affect the oscillations. And the control variables of this experiment will be the length of screw, the incline angle, and the releasing angle. And we can also see the frictions that will affect the type of oscillations. With the small frictions on the surface, which coefficients will be the 0.3358. The screws start to spin like this. But if we add in the more frictions on the surface, the screws will perform more oscillations on the surface, but the amplitude of it will decay. And for the conclusions, we have mentioned first, as the incline angle increases, the oscillations will grow because of the gravitational potential increase. And second, as the bend of the screw increases, the moments of inertia will also increase, so that causes the oscillations decrease. And for the last, as the friction coefficient increase, the screw will perform more oscillations, but the oscillations will decrease. And that's all my presentation. Thank you for your attention.
Okay. Following, we have 2 minutes for opponent to ask questions to the reporter, please.
Okay. So the observation video that you showed on the report statement, I think that the growth, the oscillations has decreased, not the growth that the report statement mentioned.
Yes.
And so could you tell me how do you define the growth of those oscillations in your mentioned in your report statement?
The group of the oscillations, I show that in this slide. And there are the group of oscillations I define is
The head of the
angle. The angle of the head and tip.
Okay, and
relevant to it.
Okay. And the observation video that you showed, which is under which circumstance in page 3?
In this situation is the very small inclined angle, so you will just perform the oscillations without sliding.
I would like to ask which incline angle that you showed in this video.
In this video, I showed is the 3 degrees situation.
And please turn to page 4. Did you think that the movement of these 2 kinds of the screw is a kind of a damping motion?
Yes.
So, as we know, that there are some characteristics about the damping motion. So, which kind of the damping motion that you think the screw is acting in this system?
In the 40 degrees, we can say that is 100.
And please turn to page 7. Could you tell me which kind of friction is acting as a side view about the screw?
You mean what kind of friction?
Yes.
Yes, it is the kinetic friction.
Kinetic friction. Okay, and please turn to page 26.
Sorry, time is up. So, opponent, you have 3 minutes to prepare. time is almost up. So, opponent, please take the stage and make presentation for up to 4 minutes, and remaining time will add to the discussion. Please start.
Okay. Honorable juries and fellow competitors, my name is Ethan Shi from Team Epsilon. I'm the opponent today to concluding problem number 9, oscillating screw. For the problem statement mentioned, I believe that the problem statement shows the main focus that they are going to focus on the growth of the oscillations and the motions on the screw. And about the growth of the oscillations, I think the reporter shows the different kinds of the oscillations, but the observation video that they show is not growth oscillations. I believe that is a decay of the oscillations. And about the summary of the reporter, and about the theory, the reasons of the oscillations were because of the tangential velocity differences, and about changing the inclined angle to see the influence of the oscillations, and they solve the equation of motion by using different parameters, and about the energy transfer, they find they explain the different kinds of oscillation is because of the energy transfer in the system. And about the part of the experiment, they have the less of the quantitative comparison between the theory and the experiments, and didn't explain the extent of the critical angle, which I believe the reporter can find it more clearly about the critical conditions. And they have less explanation about the theory results. And the analyzed method I suggest the reporter can improve is that, as I mentioned, they use the tracker to track the motion of the head, but in the oscillations, as we know, the angles that are changing over the time was also important. And I also mentioned about the oscillations were separated into several kinds. A kind of the oscillation will be the spinning of the screw. Another is the decay of the oscillations, and also the growth of the oscillations, which the problem statement is mentioned. And about the parameters, they use the inclined angle, length of the screw, friction coefficient to do the experiment to prove the equation of motion, and also write the numerical simulation of the equation of motion to do a comparison with their experimental results. And I would like to also mention about the strength and the suggestion for the reporter. About the strength, they have completely quantitative phenomenon explanation about the problem, and they have a lot of experiments to prove the assumption that they provide, and they have well modeling of the screw and have a good experimental setup. And about the suggestions, they have that quantitative comparison between the theory and the explanation. And also, the analyzed method didn't be clear explained. And they have didn't define the growth of the oscillations, which I believe is the oscillations about the head, and can't clearly describe the observations. And about the discussion for the setup, they measure the friction coefficient. I would like to talk about the friction coefficient about the reporters provide. I would like to ask about which is kinetic or the rolling friction. About the method, the releasing method should also be discussed about that the method they use will change the initial tangential velocity. And about the data analysis, they have the quantitatively found the damping coefficient. I believe it is also important. About the data, the angle and the trajectory should be comparison to each other to find the relationships in their oscillations. And about the theory explanation, there are also some parts I would like to discuss, such as the quantitative understanding about the phenomena physics behind, and the concept clarification and the quantitative modeling. And I would like to start my discussion now.
Yeah, please.
Okay, let's move back on the problem statement. So the problem statement mentioned that you have to investigate about the growth of this oscillation. So did you think you have to investigate about the growth of the oscillations?
Yes, we have done many experiments to check the growth of these oscillations.
About the oscillation? Yes. About the oscillations motions, there are some characteristics. Could you tell me some of the characteristics about the oscillations motion?
The oscillation motion, can you define that?
Okay, such as the amplitude of oscillations.
The oscillations will be the periodic motions of the screw.
Yes, I agree to the reporter. The periodic of the oscillation is one of the important parameters that the reporter should be investigate about. And I believe the damping should be also considered in your analysis.
Yes.
And so in the short question, you mentioned that it is an under damping.
Yes, because there is the constant frictions that cause the damping.
So in your could you turn the page that you show your experimental result? I believe it's page 27. Okay, and here's the experiment about the incline angle.
That's the length of the screw.
Length of the screw. So how do you compare them between the different parameters?
I just used the data graph to look the trend of the oscillations and found out that with different length of screw, the type of oscillations will be different.
So you mentioned about your comparison between the amplitude in different lengths of the screw.
Yes.
So do you think that when you increase the length of the screw, that the amplitude should completely be changed since the length, if we simplify it as a pendulum?
Yes.
So the amplitude of the oscillation, that if you choose the length of the screw, the oscillation amplitude should be changed since the initial length of the screw is different.
Yes.
So how do you choose the angle for the length of the experiment?
I choose the incline angle for to let us see the different type of oscillations. Since the incline angle will also change the type of oscillation. So I choose one to let us to see there's the two growing oscillations and three decaying oscillations to make the comparison.
So since the wooden board might not be the equal, would it be a possible factor that made your simulation different to the experimental result?
I mean the wooden board will not be that smooth.
Yes, and in your experimental result, to comparison with your simulation result.
Okay, since we can make sure that the wooden board is every part of the wooden board is will be the frictions will be the same. So in our simulations, we can this can be the result for the deviations of the model and our experience and our model.
Okay, and let's look at the simulations result and the experimental result. And let's move on the experimental result here in the 3 degrees. Okay.
Yes.
And in your simulation result about the 3 degrees, the time ended in 3 seconds.
3 seconds.
So that's your experimental result. That we choose the 3 seconds to cut it. And do you think that the periodic of your simulation result and your experimental result can compare with each other?
I think it will also have some deviations.
So could you talk about the possible reason that cause the deviations between the simulation result and your experimental result?
One is maybe the simulations I use cannot completely fit all the situation, and the second one is if we find it in the experience, I think it will be the friction coefficient on the wooden board isn't that even. So
Okay.
really close.
So which kind of method that you simulate your result?
I use Python to solve the equation of motion.
So reporters, you first solve the equation of motion for the system and you pop into Python for the numerically simulation result.
Yes.
And so for the simulation of the oscillation system, I think the damping is an important part. So Did you measure the damping about your experimental result and plug into your simulations for the comparison?
The damping for the value of the damping, I didn't measure it in those presentations.
Okay, let's move on.
Oh, okay.
So could you repeat again which kind of damping do you think?
It's the under damping. It's a constant just that causes the damping.
Okay, I agree with the reporter. And about under damping, that we know the equation of the under damping can written as the equation here. Right?
Maybe you can change another thing.
Okay, so let's just look at the equation. And so,
Sorry, I can repeat this equation here.
okay, I will write the equation again.
Okay.
So this is the equation about under damping.
Yes.
So I suggest the reporter can fit the result as the equation here to find the damping coefficient, and then the reporter can comparison between the different parameters that make sure the damping about the oscillations is differences in different conditions. Since changing the length of the screw may also change the initial amplitude about the oscillations.
Oh, yes.
And another hand, when the reporter tests the damping coefficient, they can plug into the numerical simulation to make sure that the numerical simulations will get closer to the experiment that the reporter did.
Yes, maybe I will do this in the future.
And could you turn the page that you investigate about the different kinds of oscillations, like the growth oscillations and the decay of the oscillations?
Do you mean this page?
Yes. So how to make sure that the critical angles will between the 40 degrees and 50 degrees, since that is very similar.
In the experimental result, it's quite similar for the shape of the oscillations. In my experience, I used the protractor to adjust the incline angle, and maybe the incline the exact incline angle is between the 15 and the 16 degree, but I can find it out because due to my setup isn't that.
So do you think the gravitational component in this in 40 degrees and 50 degrees is similar?
Can you rephrase your question?
Since you mentioned that the reason because the critical angle is the differences of the gravity components.
Yeah, yes.
Do you think that 40 degrees and 50 degrees has a similar gravity component?
14 and 16.
No, 50 degrees, which is
50 and
40 degrees.
I think it will be close, but the motion of the screw, I think it will be very sensitive. So if we change 1 degree, the total motions could be different.
Okay, in my opinion, I think the gravitational component in 40 degrees and 50 degrees is very similar. So maybe there is another reason that for the critical angles. So in the theoretical modeling, you have mentioned about the rotation axis of the rod. Could you turn the page of the theoretical modeling? Yes, in this case, do you think the rotation axis is time dependent, which means it will change over the time?
In my model, I assume that is the constant that passes through the central fence.
Okay, thank you, sir. Opponent, please make your 1 minute summary.
Okay, thanks for the answering question about the reporter. In our discussions, we first discussed about the different oscillations in the reporter's report, which is a growth of the oscillations and a decay of the oscillations. And the reporter finds the critical angle which will change the different kind of oscillations in their experiment. And also to quantitative comparison with different parameters, I suggest the reporter could use the fitting curves about the underdamping to find the damping coefficient, then they can compare the different parameters by quantitatively. And about the simulations and the experimental results, that there are some of the periods can't compare with each other, so I suggest the reporter can consider more parameters into the simulation to make the simulation results more similar as the experimental results. And here's my summary.
Thank you. So following is the questions from the reviewer. Reporter, please.
First, for the reporter, what's the definition of oscillation? The oscillations, I've shown that in one presentation that I measure the oscillating angle. I will use the slope to get.
Thank you. And what's the main reason for the oscillation of screw?
Because of the tangential velocity difference.
Okay, thank you. How about moments? I agree with the reporter that the tangential velocity was differences, and also that they mentioned about the target. Thank you. Will the thread affect the center of the mass?
The thread, I think it will not, because the thread is
okay, thank you. So you think it won't affect it? It won't cause another weight on the screw?
It will cause a weight, but won't change the.
And what's your releasing method? What's your releasing method?
Releasing method. I use the ruler to release. Like
so you use your hand to release the.
No. I use the ruler.
Okay, thank you. And for the opponent, do you think that the ways that the reporter release the screw will cause deviation? I think the method that the reporter release the screw will change the different tangential velocity, which is important about the.
Okay, thank you. For the reporter, do you have any theory line in your report? A theory line. I have considered. I've calculated the equation of motion.
So you can compare your theory with the experiment.
Actually, my simulation is based on my equation of motion.
Okay.
So
okay, thank you. So for reporter, when you change the length of the screw, do you also change the mass of the screw at the same time?
yes, and it will represent on the moments of
Okay,
inertia.
thank you. Please turn to page 9.
Page 5.
Next page.
This page.
No, page 9.
Or page 9.
This page. And here the direction of the friction is parallel, right? Parallel. The friction.
No, it was. It's the kind of the description of the friction. But in the real situation, the direction of friction is not given to the.
And for what's the boundary condition of your experiment?
The boundary.
There are no boundary conditions.
I describe it as the critical angle, and I mentioned it in that.
And how about maybe the friction coefficient or the releasing angle? Do you think you have a boundary condition?
For the yes, I think you have boundary
I think
condition.
for the opponent, do you agree with that? I believe that reporter have tried a lot of the critical angle and critical condition. Okay, thank you. Please turn to page 31. Okay, can you explain why the oscillation at this is
Sorry,
different?
time is up.
Okay, okay, thank you. Thank you.
So following is the preparation time for the reviewer. Reviewer, please make your review.
Hello, and all the fellow competitors. I'm the reviewer from Team Selfie. Today I'm going to review problem number 9, oscillating screw.
And here's the product statement. When placed on its side on a ramp and release it, a screw may experience scoring oscillations as it travels down the ramp. Investigate how the motion of a screw as well as the growth of these oscillations depends on relevant parameters. And I'm going to mainly focus on when will the screw experience scoring oscillations and how will relevant parameters that will affect the oscillation of screw. And here's a review of the reporter. First, in the phenomenon part, they have shown about the oscillation of screw, and in theory, they have talked about the equation of motion and also the energy transformation. And they have done the experiment about different parameters like the inclination angle, length of a screw, and also the friction coefficient. Then the conclusion. And I think the reporter did a great job demonstrating the phenomenon about the oscillation of the screw, and also he has shown the clear experimental difference, and also I think they have a very clear theoretical model. But the boundary condition isn't considered in their report, and also they have a low comparison with the theory, and also I think the explanation of overturning is the explanation of overturning is too little, and also they didn't mention about racing methods. And here's a review of the opponent. I think he did a great job on discuss about assumption, and also he has clearly understand about the reporter theory, and also he has pointed out reporter experiment error in her theory part and also experiment part. But I think he did a good well about discussion the boundary condition of the phenomenon that the oscillation of screw, and also he didn't mention about the physics behind different parameters, and he also didn't mention about the energy transformation when the potential energy decrease. And here's the discussion part. The opponent asks, how do you consider a characteristic of a screw? The reporter answered, we didn't compare the amplitude of the oscillations. And the reviewer thinks that we believe that we should investigate on amplitude for the maximum angle and the acceleration in y-axis, angular acceleration. And the opponent asks, what caused the deviation in your experiment? The reporter answered that error parts come from the wooden ramp surface, and the reviewer believes that it might be caused by the initial condition for the releasing method, and I suggest that they're using an electromagnet for the releasing. And I asked about the reporter and opponent. Is the direction of friction parallel in the two different contact points? The reporter answered no, and also the opponent would agree with the reporter, and I also agree because the velocity on the different contact point is different, so of course the friction is not parallel on different contact points. And I also asked, will the thread affect the contact points or change the location of center of mass? And the reporter says no, it will not. And also the opponent agreed with it, and I also agree. And here are some points about the discussion. First, I think the reporter didn't define the sliding and the oscillating clearly, and also in the theory part, I think he didn't have explain more about the energy transition, and also the opponent didn't discuss it about it more, and also the difference of two contact points. And I think that when the reporter changed the length of a screw, it also changed the mass of the screw. So I think it should be controlled. And also about the deviation analysis, I think he can explain more.
The time is up. Following is the time for reporter to make a concluding remark, please.
Okay, I'm going to conclude my presentation. First, I would like to thank for the opponent and the reviewer for such a pleasant discussion. And in the discussions, we have talked about the definition of screw oscillations and the kind of frictions will be the kinetic frictions, and also the damping. We can the opponent suggests us can measure the damping to make our simulations more completely. And the rotation axis, and we also talk about the rotation axis will change over time. And the reporter thinks that in your model, we just assume that is is fixed to the pass through the center of mass. But in the in the another situations like it starts to spin or like reverses is overturning, the axis of it will I think it will change. And for the fixes, we agree with the opponents that we can do more parameters in the experiments to measure the more boundary conditions. And we can try to use different releasing methods. Is because although we try our best to not let the releasing methods to change our result, but I think it will slightly have some deviations from our result. And for the page 31, the graph on the left-hand side, which we reverse as mentioned, it is performing the spinning. And finally, I want to talk about the energy. Why I don't use the energy transform to analyze the motions. That's because that if we need to calculate the friction, we need to calculate the total path of it, and it's very complex to calculate it. So I just use the initial motion for simulation. Thank you for listening.
Then we move on. I would ask the three presenters stay on the stage, and jurors, you can ask questions. Any questions? Yeah, please. Yeah.
Okay, I would like to ask the reporter, you changed several parameters,
Yes.
but can you fix the length of the screw and by changing some parameters that you can observe some differences in the oscillation period?
During the period will be different.
For example, maybe you can, for a screw there are different threads. Yeah. For the different threads, I think that the friction and also the torque also influence your results.
In my experiments, I didn't try the use the different threads to do the experiments, but I think
I think that's all. That's okay. You didn't change. Right?
So how about you?
I think to fix the error about the length of the screw, we can make the reporter can use the damping analysis to find the damping coefficient, to compare with the different parameters, or found the period of frequency.
The reporter had mentioned about the screw oscillating because of the center of the mass is not in the middle of the screw. So I think when he changed the length of the screw, he also changed the mass.
Okay, thank you. So more specific, if I fix the length but I change the thread, what will happen?
I think it depends on how the parameters will affect the center of the mass.
And in the video that the reporter provides, you can see that the screw is now falling in a vertically. So I think that changing the thread will changing the trajectory of the falling on the rack.
Thank you.
So
how about the
when we change the length,
fix the length.
Fix the length, but the threads change.
So we fix the length of the threads will change, and the thread will, the amount of threads will, maybe it will change the mass of the screw, so that causes the center of mass to, the positions of the center of mass change.
Okay, thank you.
So if there are no further questions, oh yeah, please.
I would like to ask the reporter, what kind of friction are you assuming for your simulation? Does it depend on velocity, or it is independent of velocity?
Okay, in my experience, I assume that the friction is the kind of friction. But in the several conditions, like in the previous, in the phenomenon part, I showed the oscillations without sliding. And in in that situation.
But my question is, what kind of friction do you assume? Does it depend on velocity or not?
That will depend on the sliding velocity. If there are no sliding velocity, the screws will perform the pure rolling. So
The question is the friction you consider is a function of the speed or not.
It's not the function of the speed.
So it's just a constant, independent of velocity.
Yes.
Okay. And in such a case, do you think the term under damping or over damping still apply? This is a question for all the three companies.
I will reply to this question. I think that that kind of damping will be the under damping, since I assume that the friction is a constant.
So you say that the friction is in the cause of the damping.
Yes.
Okay.
Okay. And the opponent?
About the damping, I think the head of the screw will move back and forth at a point, so I think it is a kind of under damping.
Okay.
I think because the exponential cancel is under damping.
Okay.
Okay, a short question, please.
I have a question for all three teams. It's about energy. So you talk when the scrolling, so which means that the oscillation energy is growing, but simultaneously it is sliding down, which means that the kinetic energy is growing. So does it violate the conservation of energy? So let's start from the reviewer. Reviewer first, and then reporter, and finally opponent.
I think when the screw is
Reviewer first.
when it's oscillating, and the potential energy will change to a rotational energy and a translational energy, and because the rotational energy will cause the friction, it's like the energy dissipation, and so that the rotation and
Please, short answer.
okay.
Energies.
The potential energy turns to the rotational energy and the rotational energy.
Okay.
No, translational energy. For my analyze, the gravitational potential energy will provide the whole energy for the sliding and oscillating and rotating. Also, the energy will be taken because of the frictions. So the jury just mentioned that when the screw slides down, the free oscillations will be
Okay.
So I think the potential energy will transfer into the three parts of the kinetic energy, which is the rotation energy, oscillating energy, and the slide kinetic energy in the system. And I think the energy will decrease because of the friction, but we have to find a trajectory of the friction to make sure how it works on this system.
Okay. So I think we move on to the scoring part. Okay, it seems all the scores are ready. So we start from the reporter. Please show your scores. It's 5, 7, 7, 6, 8, 6, 7, 8, 6, 7, and 7. The scores for the opponent, please. It's 5, 8, 8, 8, 8, 7, 7, 6, 7, 8, and 7. And the scores for the reviewer. There are 6, 8, 7, 8, 8, 8, 7, 7, 7, 8, and 9. So we need some comments. comments from the high and the low scores, and if we have more time, we would like to ask some comments from other jurors. So for the reporter, we have 5, 3, 6, 0, 7, and 2, 8. So we start from the 5, please.
Okay, for the report, basically the lower grades comes from the science communication. So you did good, basically you have good mark. Basically you have good experiment, but when you talk about your results, you just say that this is the formula, and also for you didn't introduce the coordinate system. Where is the x and y? Is it on the sliding plane, or is it in the laboratory, usually the flat plane and so on, and such that we cannot understand what happens really there, and that is one. And secondly is that for your comparison between your experiment and simulation, we couldn't directly see what happens between the two, so it is hard to follow the results and to understand all the ideas that you bring us. So that is the big drawback here.
Okay, so how about the 8, Professor Peng? Would you like to give comment?
I think overall the experiment shows the three different phases: decaying, growing, and just flipping. I think that is quite interesting to see this effect. But I think I just give 8 because I should give better marks, but you ignore the XY direction. What happens in this case, how the XY changes, because the motion along the plane will affect the motion of rotation. I think you should put this correlation together, and then you can get better marks.
Okay, thank you. So for the opponent, we have a 5, 1, 6, 0, 7, and 8. So we start from the 5.
So for the opponent, the very bad point is that you didn't discuss anything during the 10-minute discussion. So you just play around and ask questions, but never go into any physics. That is very bad. And secondly, for the questions asked, so you almost focus many articles stuff. So never that did not help to clarify anything. So that I gave you overall 5.
So for the opponent, you want to give some comment?
I give opponent 8 because I think the presenter is very good at carrying out the discussion, and that was very manner, and he understands the details.
Okay, thank you. So for the reviewer, we have a 1, 6, 1, 9, and equally 7 and 8. So start from the 6.
So for the review, actually, basically for the questions they ask, for questions part, there are one type of them are concentrating on technical stuff, and also for these questions, you didn't go into details during your concerning maybe
That is the missing point or something. So
which therefore so a little bit as I mentioned, so normally it's peer review, but on peer review is 7, so from that you lower grades from me, that is.
So any further comments?
Yeah, I give 9. Apparently, not because he is the male student on the stage, okay? I think he asked some questions I also want to ask. For example, the initial condition, the contact points, and also related to the moment of inertia. Those factors are also very, very important in the discussion. Although the time is limited, he didn't go into the detail. However, I think he still did a very good job to point out those points. Thank you.
Okay, thank you. So since there are no further comments, okay, so I would like to close this round and take 10 minutes break. So please come back to the seat.